robotics lab at ITMO University. And I'm very happy to say this. Stefano is an IEEE fellow, and for a long time he was an officer of Robotics Automation Society of IEEE. He is vice president for research of EU robotics, and a very long list of very prestigious awards which Stefano obtained. But I would say that Stefano is fantastic speaker whose lecture always very interesting, very attractive, and I'm very happy that we will have we can see his lecture now. So I see that we have amount of participants increasing. It's very good. And let's go, Stefano. Let's see your presentation.
Hello, my name is Stefano Stramigioli. I'm from the University of Twente, and I'm also partially affiliated at the ITMO University in St. Petersburg. It is my great pleasure to try to give you my plenary recorded, considering that due to Corona-19, unfortunately, ECC 2020 will not take place physically. So I want to talk about physical control for physical systems. And this is I will try to explain what it is, why the way I use it, and why you should use it in the first place. First of all, I want to introduce my main affiliation. So I'm, as I said, from the University of Twente, which is in the east of the Netherlands, very close to Germany, and is one of the most entrepreneurial university, certainly in the Netherlands, the most entrepreneurial, and one of the most in Europe. We have more than 900 spin-offs, some of which you definitely know, like Booking.com, for example. And we have also Max Planck Institute on fluidics, and Fraunhofer, and these German-related activities are, of course, thanks to the fact that we're very close to Germany. This is just a glimpse of a number of the spin-offs. Other big ones are Takeaway.com, which I think it is the biggest delivery now of food in the world, even more than Uber, I heard, and so many others, some of which I will talk about it later. So I have the pleasure to lead the group RAM, which is called Robotics and Mechatronics. Was originally a group actually on control, but I steered in more and more in robotics, and the breadth of the activities increased. So it's a big group. About we have a running budget of 4.5 million euros, 25 to 30 PhD students a year. And what is special that we also have a lot of clinicians part-time, because for a number of the activities I'll show in a moment are really medically related. And recently Antonio Franchi joined the group. Antonio is a very good scientist working on drones, aerial and swarm robotics, and we are very happy that joined the group since recently. So the group has a lot of knowledge in modeling, control, embedded system, imaging, and other things. And the application field are mostly healthcare, inspection and service, and other activities outside this scope, which I also will talk about it later. This is a glimpse of the activity. So we have a broad spectrum from very conceptual work to very practical work, and work which is completely domain independent. So you should think about, general software architecture or conceptual system and theoretical developments, towards something which is very much related to a specific field. Like, for example, if you work in the medical field, you really need to have knowledge about the field itself. And we have a lot of activities, which have been recognized with a number of awards and a number of patents for which we start also a number of spin-offs. But I will not talk about this stuff in this lecture. So I want to reference first of all a colleague from Stanford to introduce the things I want to talk about. Nowadays everybody's talking about AI, artificial intelligence, and very often the general public at least doesn't even know what it is all about. And it was already in '88 that Moravec, colleagues from Stanford, made this statement by saying basically that it's actually relatively simple to automate things which human thinks are very complicated, like playing chess, for example, or Go recently. But it is extremely complicated to create machines that can actually repeat very simple tasks that babies, for example, do when they are born. So what I'm trying to say is, everybody's talking about artificial intelligence, like computation has, this big potential, and it has definitely. But if we scale the human body on the basis of the volumetric quantity of the cortex of the brain, which is actually used for a certain specific part of the body, so you get these pictures, which is a cortical homunculus. So what you see, for example, it has very big hands, and in fact, a big chunk of the cortex of the human brain is actually used to steer and sense the hands. And actually, that's the very reason why, in evolution, the human species have, been actually evolving faster and more intelligent than other species. So what I'm trying to say is that very wrongly, in my opinion, well, it's a fact that, people talk about AI like, AI is going to solve everything. And what I mean AI now is really more the computational side, without considering that actually the motoric and dexterity of interaction that humans have is far more complicated than that are a lot of computational tasks. And this is something which is really completely underestimated also from political planning on research and things like that. And of course, the real sweet spot is what I call physical artificial intelligence, which is exactly the intersection of AI and robotics. And where, the two things, the computation, the physical interaction, meet. Talking specifically about robotics have passed from, its early stages in which we had machines that were stiff, high speed. The environment was very structured, very far from human, to a situation in which we really need machines which are mechanically compliant. The design intrinsically has to be mechanically compliant. Doesn't have to be often very high speed, low speed is enough, but completely unknown environment and interaction with humans. And in order to tackle this kind of problems, you really need to think differently. You need new control strategy, new actuators, new materials, new performance measures. And the safety for the human interaction starts becoming a major concern. I just want to show you something here. So what you see is, we are far from being able to build robots that can do what these humans can do here on the left side. And at the same time, if you look at birds, and I will come to that back later in my lecture, birds are amazing. And if you compare this with, some top planes that have been developed, like the blackbird is probably one of the fastest plane, or the fastest plane available. It actually flies at 32 body length per second. Once a swift, which is a little bird, can fly at 40 times its body length per second. And also concerning agility, if you consider Douglas A4 Skyhawk, which has a rolling rate of 720 degrees per second, there are other born swallow birds that have a rolling rate of 5,000 degrees per second. So you see that the way to interact with the environment, we are far from being close to having reproduced that. So what I want to try to bring you is really a paradigm shift. So This is what you see here is just a little game that I play all the time when I give this kind of lectures, is that, what is this device is called the dovetail. So you have basically two parts, the red and the gray one, they can move relative with respect to each other. You see that you have basically it's used in all kind of appliances. You have 1 degree of freedom is free to move. All the other 5 degrees of freedom that constrained, because two rigid bodies are connected by 6 degrees of freedom totally, are constraints. And then if I would say, most of the time you say, well, what happens? Can these two parts now move with respect to each other, the red and the gray? I'm pretty sure a lot of you are thinking, oh, they cannot move like that. Well, it turns out that definitely that is the case. These two parts can move. And of course, I ask, what are the getting out the symmetric other rotation of 90 degrees? Are there other ways that this could move? And the answer is, again, yes, there are many, many ways this could move. And for example, what you see here is one of the other kind of motions. And actually, there are many more motions that are possible. And what I'm trying to show here, and this is yet another one, that what I want you to try with this lecture is try to break out of your partners and try to think out of the box. Because what happens in what I just showed you is that you see things and you are trained in a certain way, you see things in a certain way, and it's very hard to get out of that way of thinking. So in the example before, by looking at the surface, you make directly draw conclusions of the whole volume of the two objects, which of course are not the case. So that is why I wanted to show you this. And what I want to talk about is interaction. So what if you want to model and control systems that interact with the physical world? And I would like to cite Ludwig Wittgenstein, who made a statement which is pretty known. It says, what we cannot speak about clearly, we must pass over in silence. And this is something that a lot of politicians actually should write it on their bed, because a lot of statements are made without basic on knowledge of science. But what I name it here for is that to talk about robotic soft compliance interactions and impacts and all the things that actually I want to address here, we must use the right tools and language. And I am absolutely certain that physics and port-based and energy-aware methods are the things to be looked in this case. All the work I'm talking about is actually started more or less on a work I did in the past with Bernard Maschke and Arjen van der Schaft, who have been incredible coaches for my work from the very start in '98. And then these things have evolved in a number of other concepts which are developed with a PhD student of mine, Vincent Downman, relating to what is known as the energy router, and a lot of other things that came out from this line. So these are the number of the ideas like energy tanks and other things which are used more and more now in the robotics field, at least. I want to stress first the importance of energy and the geometrical way of addressing robotics before starting in more details. Important to realize that robots and interaction follow the law of physics. And very often, especially in control, in system theory and control, most of, I would say 99% of what is done is not really looking at the use of energy and the physics in it. So it's abstractly things are considered like mathematical models, and unfortunately, if there is no relation with energy, there is very often no way to work in all situations during interaction, for the reason I'll say later. Robustness becomes an issue. The environment cannot be properly modeled by definition. So if you have a system which interacts, a system which is controlled, that interacts with an environment which is unknown, and interacts means physical interaction, when the system interacts, the environment becomes part of the dynamics of the system. And therefore, there is actually no way to know this environment ahead of time, but in any case, you want to be able to stably interact with this environment. And these are the kind of problems I'm looking at. And unexpected behavior is always there. Very often, for example, in the old days of robotics, people that wanted to study the interaction of a robot touching a table, they were making hypotheses of the table being linear, having a certain stiffness and a certain damping, and then they could prove stability. That's not really, in my opinion, of big value, because a table is not linear, it doesn't have a certain stiffness, and the robot should interact with any table in a certain way, and humans are definitely able to do that. So these are the kind of things I want to look at. Passivity, or better, energy awareness, because very often people wrongly say that passivity is restrictive because it restricts, it's conservative with respect to what you can achieve with concept like passivity. I strongly am against this way of thinking, and that's why I use more the concept of energy awareness, because you can track energy flows perfectly, keeping the advantage of all the ways, all the methods that are developing passivity, but still being as open and as free, as not restrictive as in all other situations. And if you do that, you can track and control energy flows. You have never problem with stability. You can be very easily robust. You can couple in a very elegant way discrete and continuous time. You can handle time delays without any problems, etc., etc. Another thing which is very important is geometry. Very often, a lot of things are done just by not using geometry, by just using algebra and equation. We are looking at the geometry of things, and then you get very often complicated equations, solution dependent, which are dependent on coordinates. Even things like taking eigenvectors of an inertia matrix. That's been done in robotics many times, and it makes no sense whatsoever from a tensor point of view. So that's all this non-physical nonsense that you see in projection and other things. And then you result in problems like having singularities. So the robot, you have to be careful that it doesn't get close to singularity due to the coordinates, and unexpected instability. Instead, if you do you tackle the problem right, so looking at geometry, things like tensor calculus, Lie groups, that's the proper geometry. Then you can you have a simple description. You are always coordinate invariant. You respect the physics. You have no singularity, and you cannot make mistakes that you would make if you wouldn't do that. So there are a lot of big advantages for that. And here's just an example of the important geometry and coordinate invariance. It can be easily seen in a lot of examples. For example, eigenvalues or determinants, as I said, of inertia matrices. Manipulability in robotics has been something that is completely wrongly handled. And there are a lot of examples on projection and other things that I mentioned before. So now I want to talk about energy awareness as a basic way to tackle the robotics interaction. And I think that this, as I said, is the answer to question of natural and safe physical interaction. So first of all, let's look at the modeling side. What is what I call port-based thinking? And first, what is it and why is this useful? Now, let me start with this little example. So what you see here is a voltage divider in which you have now two impedances. And very often people say, okay, if the load is an input in impedance, I can easily write the transfer function from input to output, which is reported here. And this is, a typical school exercise, I would say, academic exercise that the students get. And now if you go to students and you say, now let's take now the V in versus V output of this network. I am pretty sure that a lot of students would say that is what it's going to look like. But of course, this is not the case, because the transfer function was written under the hypothesis that the load was an infinite impedance. But now the second network has not infinite impedance, and therefore the first network does not see an infinite impedance. So this is absolutely not the case. Now, what can we conclude from this example? Now, I think that the issue is that, with physical system, signal modeling, as it is done in most of the cases using, for example, transfer functions, is often not suitable. You can make a lot of mistakes. Physics and the physical energy governs the dynamics, and therefore, and the fact before is because, of course, there is a bidirectional effect of the two networks. Always you have a bidirectional, in general, nonlinear effect, and therefore, to model control real open system, signal modeling is often not the right solutions. Another example is, for example, a DC motor. There are a lot of basic books of modeling and control, which talk about DC motors, and they talk about an electrical constant and a mechanical constant of DC motors. And I remember when I was a student, I thought that there were two different numbers. This is, of course, big nonsense. It's about the same physical thing, which is called a gyrative effect between the electrical domain and the mechanical domain. And therefore, the mechanical constant and the electrical constant are the same physical thing. And of course, by changing units, you could change the value of it. That doesn't matter, but it is the very, very same thing. And especially in robotics is interaction of multi-domain parts. So you need really to tackle things different. And you need the concept of what is called port-based way of thinking. Now, so this is a schematic idea of a robot, and the robot interacts with the world. It can be, a wall, can be a hand. And the power port is basically the way you describe it, the concept that you use to describe the interaction between the two systems. And as is indicated here with the red arrows, it is always bidirectional. So it can never be in one direction only. It is always bidirectional. So what is a power port? So if you consider now a controlled robot and the environment it touches, these two arrows will be represented by what are called conjugate power variables, so forces and velocities. In the scalar case, it would be really a force and a velocity. In a multi-body case, this would be Lie groups, and I'll come back in Lie algebra. I'll come back in a second. But and the environment is, in general, is nonlinear, is unpredictable, is greatly varying. So, but once the control robot touches the environment, the connection of the two systems becomes one single system. The stability, the dynamics, everything that happens is actually dependent on both. But very often we do not know the environment ahead of time. So how can we cope with that? And that's what I want to show you. More formally, a power bond, if you take two subsystems, system A and system B, these two variables, which are basically shared, if you wish, by the two, are called, in general, efforts and the flow. And they are two elements that belong to vector spaces in duality. So if you know the efforts and the flow are scalars, there's not really big problems. But if the flows are, for example, vectors, the efforts will be linear operators on this vector space. So it's a really dual space. And you also can go, as I'll show later, the efforts and the flow can be also infinite dimensional spaces. And then duality is also well defined in that respect. And in general, this is a causal. So this is a notation which is used in bond graphs. So the direction of the arrow is basically giving you the direction of the positive power flow if the application of the effort on the flow is positive. Suppose that, the effort applies to the flow gives you 5 watts, it means that in that moment in which these two variables have that value, you have 5 watts going from A to B. If there would be minus 5 watts, it would be the other way around. And in the notation on bond graphs, then you have also the causal stroke, which is basically a line which you can draw or not, depending whether you want to show the causality. And that shows the direction of what is the effort. So in this case, for example, if the causal stroke is on the side of B, it means that the effort A provides the efforts to B and B provides the flow to A. You can never have, the dual situation would be if the causal stroke is on the other side. Okay, so that then in that case, B provides the efforts to A and A provides the flow to B. And it's never possible that either A or B would set both variable at the same time. That goes against any physical principle, because that would mean that independently on the other system, a system can set the efforts and the flow, which means the power, you could extract any power from the other system that you do not know. And that goes against any meaningful physical reasoning. So this is an example of what you have in this, what are the efforts and the flow. For example, in the electrical domain, you have current and voltage. Should be, the flow geometry would just be a scalar, not big deal. Then you have rotational mechanics. You would have SO3. So this is actually a Lie algebra, SO3. If you get to multi-body dynamics, you would get Lie algebra, which is SE3, which is a 6-dimensional Lie algebra. And if you go to continuous mechanics, you would have the space Grassmannian algebra of forms. And the dual would be the n minus m forms is the flow are the m forms in an n-dimensional space. We'll briefly go to that at the end. So these are really a Lie group algebra. So physical modeling is based on a number of concepts. The first thing is what is called the Heaviside principle. Basically, and that's the reason why you're modeling power ports. And Heaviside says basically that, energy cannot disappear in one point and appear in another, but needs to traverse the space in between. And therefore, you can model the transfer from one part of space to another part of space by having a port in which the energy traverses to. And why do I care about energy? Because I'm talking about modeling of physical systems. So energy is a kind of Esperanto concept that connects all physical domain. Furthermore, energy can be stored in a reversible way, elastically, inertially, magnetically, or can be dissipated, or better, irreversibly transformed. And that would be the concept of friction, ideal damping. Of course, energy cannot be dissipated because for the first principle of thermodynamics, only free energy can be dissipated, which is a Legendre transformation of the energy. And energy can be distributed or shaped. So, you have mechanisms like transmissions, gears, lever arms, are a way that you can basically transfer energy from one part of the system to another, and the power continues. So, in principle, the concept of distributed shaping of energy does not change the energy content. All these ideas are the things I will talk about are actually reported in this book, which was actually a deliverable of a very nice project we had with a number of distinguished colleagues like Ariel van der Schaap, Bernard Maaske, Romeo Ortega, and a number of others, and a project that I coordinated many years ago. And this book was basically the final deliverable of this project. And basically, this way of thinking, you should thinking as is in the scheme here on the left side. So you basically, you should think about modeling as an interconnection of parts, in which the yellow power port would basically, you could look at an analogy of a fluid. So basically are like pipes in which water can flow. Water in this analogy is nothing else that energy. And then you have a power continuous interconnection, which is represented mathematically by a Diera structure. And it's basically the water that comes in there has to go out. It cannot stay there. It cannot be stored there. And then you have storage elements like sea, like a balloon, which can be blown up. So the water can come in and be stored there. Or it can be irreversibly transformed to entropy. So that's the R element, the dissipation, in which the water coming in from R cannot go back to the system and is basically stored in the entropy, which can only increase from a thermodynamic point of view. And thanks to these things, you can model a robot of any complex mechanism as an interconnection of, storage of inertia, for example, of kinetic energy, storage of potential energy, irreversible transformation to heat with dampers, and the rest will be interconnection. And then you have open elements, and this is very important because it's the core I will talk about, you can then couple this mechanism, this robot, to a motor, which will, either supply energy or subtract energy. And this is most important, where you see the sand, this will be the part in which the system will interact with the world. So there is a control port and there is an interaction port. And this system can be then simplified again to this blob of DIRA structure, an element which is storing energy and an element which is dissipating energy, and would have two ports which are open. They can be interconnected to, in this case, motor and to the rest of the world. Now I want to cite a conjecture. And this is the major point of the whole work I want to present. To ensure stability during any interaction, control needs to be implemented by interconnection, either physically or by control. There is no other way. This is the conjecture. Now let's try to understand what I'm talking about. What you see here in the blue is basically the system, the general robot I want to control. So what I can do, I can say, I can do control in this way. So I could basically modify the design, which would mean, for example, that's one way of doing control, is instead of doing calculation, to basically attach springs here and there to modify the dynamics of the system. In the schematic way I introduced, this would be basically to create another power continuous interconnection, putting other parts in which energy can be stored, maybe some other things which can be dissipated. And then this interconnection would then result in a new system, which would basically say, okay, I put, for example, a spring between these two links of this robot. This is one way to do control by interconnection. In this case, the interconnection is the physical interconnection. So examples of this are given here. For example, this work, which we did with Sambai Kim of MIT on the cheetah, basically was to on the spine, it was one of the first design of the cheetah, to put a spring to basically create the coupling between the locomotion of the front leg and the back leg and optimize the energy exchange. So you basically physically shaped the robot itself. And this is, by the way, something that we are doing with ITMO. So this is in the lab at ITMO. So this is a design that we actually originally developed in Twente and has been adapted at ITMO. And this, what you see here, is developed only at ITMO. It's a very nice design in which you want to try to optimize the design in order to create the resonance of the oscillations. Okay, and as you can see here, this is the intrinsic physical design which actually will allow to build a complete cheetah. So then next, another way of doing control, instead of only physically controlling like this, what you also could do to say, okay, you want, for example, to inject damping. So physically, you would like, for example, to create damping in your system. You can easily put a physical damper, or you could build a device which extracts the physical energy from your physical system. And that energy, instead of a damper creates heat and is thrown away, but you could build it in a way that this energy is basically extracted, stored somewhere, and then used again when you need it. Because, of course, it would be kind of waste if you just throw the energy away, which you could use it later. Now, this is, for example, what we developed in Twente many years ago, this prosthetic device, which is pretty unique in the world, in which you see this vertical element, which basically is an elastic spring. In this phase, the kinetic energy of a lower leg is stored elastically and then latched. And then in this phase, then is used to create the push-up for the energy of the locomotion. And the patient, which is a transfemoral amputee, knee would recover 80% of the energy which would be otherwise lost. And this is done with many other kind of devices, knee prosthetic devices for transfemoral amputees which are out there. So you can basically build a device that, that spring basically it behaves like a damper, in which at the end, when it extracts all the energy, it just latches, and that energy then it is reused as a storage injection of energy in the next phase when it's needed. Another way of doing control by interconnection is by computation, right? So you really want to put a controller that actually it interacts with the system, but then via the concept of the port as introduced before. And then you get here to a theorem and the passivity control robot. Basically, what you can formally prove, so you see here, the context which you are analyzing is you have a system which is this orange blue one. This is the robot that you want to control with a controller, and this robot interacts with the environment which is not known, and it can be formally proven that given a non-passive system. Here, control robot. So if you look at the sigma CR, so the control robot is non-passive, okay? It is always possible to, and there is a constructive way to do it, to have a passive environment, to build a passive environment such that if the control robot would touch that passive nonlinear environment, the system will be destabilized. And this is, I think, is a very fundamental reason why it means that the system, seen from the interaction port UI, should be, by design, always passive. And the energy that you can extract from the system should be always lower bounded. Therefore, then, that is the very reason why the control of such a system should be done by interconnection and not by just state feedback, in which you measure things in one point and you actuate things in another point. So in a system, in a way which is called non-collocated, because that would cannot ensure that the system seen from the interaction port UI would then be passive. So how can we tackle that? So what we can do is the following. So we have the system, we have the environment, and if we want to control in this way, so what we want is, first of all, if you have a robot, you want to have actuators. Actuators are basically the transducer that transform the electrical power to the mechanical power for a robot. And often, and this is another thing that I've been pretty active, and there are a lot of people very active in robotics on this topic, which was actually started in a European project that was coordinated by Antonio Bicchia, who I was part of. It was called V-Actor, and the contribution and publication in the world has increased enormously during that time. And basically, variable compliance actuators are not just motor that transduce a current to a torque, but they can have physical internal dynamics in compliance and damping. For example, muscles of humans are kind of variable compliance actuators because they have an intrinsic compliance that can be modulated by the co-contraction of muscles. Then, on the electrical side, you would have power amplifier. And this is where things can go wrong. So basically, what happens if you have actuators, variable compliance or not, and you have power amplifiers, the power amplifiers basically suck the energy out of the power plug and put it in your system. And in principle, for the context of the control that we have, the energy which can be extracted from the power plug is infinite. So if you do not control the system properly, you can get instability because the energy which can be subtracted from the power plug and therefore go through the line from the energy supply to the environment can be unbounded. And if you do that, you can have instability for the reasons said before. But of course, how much energy can be extracted is done by control. So this is basically the continuous time system in which you have, everything which is here is really pure energy. But if you go to the red kind of bonds, then you have control. And normally what people do, they measure something in the system and then actuate the power amplifier. And this is, in general, not the way to do it. For the reason I said, because, you have no way of tracing how energy can be bounded and be kept bounded, lower bounded from an energy supply to the environment. So instead, what I suggest is do it differently. Because what you want is that the virtual energy flow, which you can then compute via the red bond, should be always equal to the physical energy, which you actually extract from the energy power supply and you add to your environment. If you manage to do that, then you can develop a controller that will have a lower bounded energy and therefore will prevent the environment to be able to extract an unbounded amount of energy and therefore become unstable if something goes wrong. So the first thing, of course, when you want to do digital control is the concept of sample and hold. And you need a way, of course, because there is something that can go wrong because continuous time and discrete time there change. And, it is very important to do it right at the very level, because otherwise you would lose this consistency purely due to the fact that you go to discrete time. And there is a way to do that, as I show in a moment. Once that consistency is correct, so that that the energy is consistent there, what you can do, you can develop a controller which has all the features of power port-based thinking, port Hamiltonian kind of modeling, in which you can prevent that the energy extracted is unbounded, and a supervisor that could inject energy whenever needed, but then on a lower sampling rate, for example, so that you, in every instant of time, you would track the energy flows in your system. That's the core idea. Now, how can you do this? So this is a discrete time part. Well, the gray part between the two is one important major issue, but it's very easy to be solved. This is called passive sampling. So what you see here is the interconnection between the robot and the controller. What you see in this causal situation is that the controller provides an effort to the robot, and the robot provides a flow to the controller. And we know that the port, this product of these two things, in the continuous time, should be power. In reality, what that means is that ED, without the bar, ED, is actually a torque, for example, on a joint of a robot. And FD would be a velocity, because their product is power. The torque you apply to the joint and times the velocity is power. And the question is, of course, what should be ED bar and FD bar be in order to keep a consistency of the energy? And this is the game. If we use a zero-order hold, we know that if our digital controller provides a certain value, that will be held constant for a sample interval. So we know that ED of t will be equal to ED bar of k, where k is the discrete time, for a certain interval. Now, what is the quanta of energy which is then exchanged between the controller and the robot? Of course, the energy in the robot is physical, because you apply a physical torque which is generated from a current, and the physical energy comes from the power socket. But the physical quanta of energy will be nothing else than the integral of the power from kt to k plus 1t. And this will be the product of the two variables. But considering the fact that we use a zero-order halt, ED bar is constant and can go out of the integral. Therefore, you're left with the product of ED bar times the integral of the physical velocity of the joint from one instant to the next one. But there is no better integral than physics. So the integral of velocities is the change in position. So extremely simply, you see that not an approximation, but the exact quanta of energy, which is physical energy, not virtual, physical energy, which is supplied to the robot or extracted, depending on the sign, is equal to the torque that you set for that sample interval times the difference in position that you had between the beginning and the end of that sample. Therefore, a posteriori, you have an exact measure under the assumption, which you can relax by doing some robust analysis, of measuring the position properly and actuating the force properly, that the value that you actuate is the one. You can basically ensure, you know exactly the amount of energy that you gave to your robot. And that's the key. So here what you see is something that actually, this is very simple, it actually works. So you have here a 1 degrees of freedom kind of control system, kind of PD, done at 30 Hertz sample rate. And on the left side, it is done, let's say, in the naive way by using signal way of thinking. And on the right side is done with using port-based kind of concept. And you see that, you know, you can interact and things are perfectly stable because the energy, there is no spurious energy which is injected in your system due to the fact that you are using sampling. The fact that you have this consistent way of sampling and actuation solve the problem at once. Now, I mentioned it before, you can also put energy in your design, and this is actually the project Viactors that I indicated before. So you can basically look at the actuators and how to basically engineer the system and make it smarter on itself. And these are some of the things, for example, that we did in Twente. We are now, as I mentioned before, trying to build a quadruped version of this at ITMO, at St. Petersburg. And this is a robot which actually basically doesn't have any control. So it has a front side, a back side, in which there is a little reaction control that once the energy of the spring is reach a certain constant, it basically loads the spring again. And there is a spine which is elastically loaded. And just by designing it properly, it can locomote forward. You can also build actuators, different time. This is more design that depending on the flexure that you have, it will basically is able to change the stiffness just by, for example, moving this, what is called hypercycloidal mechanisms. And you basically then can also make the clutch and release the way it moves. This is a patented actuator, which is a very nice design for repeating, to really create variable compliance by means of design. And then you can also use, smart design to basically create things like these drones, which actually interact with the environment and can basically scan virtual surfaces. So this is really our all example of smart design, or these things that can absorb, which was given the best paper award on the robotics letters a few years ago, in which the system basically arrive at maximum speed without any problem, absorbs the energy and can leave. This methodology can be pushed much further, because you can basically, with this idea, solve intrinsically complicated problem in a very easy way. Suppose to have an environment, and this is related to another project that we run, SoftPro, in which you have a mechanisms in which you have a number of actuators, and these actuators have a bus in which they have different communication delays, and you have you want to basically be able to control a very complicated systems with distributed architecture and prevent that becomes unstable. Well, there are ways to basically extend all this paradigm in a way that you basically, if you would build, for example, a humanoid, so a very complicated robotic system with a lot of actuators, that you would be able to ensure a stable behavior with any passive environment in a certain way, even if you have multi-sampling, time delays, computational jitters, and all these kind of things. I have no time to go into it, but I just want to point this out because it really shows that these very simple ideas are actually solving problems that people think that are still out there, by the way. This is an example of something related to that, in which a robot is basically moving and he wants to interact. It will interact with a user. You can stop it whenever you want. You can basically prevent that it jams. And this is a very simple example of how this could work. What you also could see in the video, if you can look it on internet, it shows also some other effects in which you can modulate the damping, the stiffness, and you can make it very safe in all kind of interactions to prevent any kind of problems. This brings me to my conclusions. To be able to stably interact with an unknown environment in all situations, you need energy awareness kind of methodology. And to retain stable interaction with time delays, varying sampling, distributed architecture, you really need a paradigm which allows that, makes that possible. And the only way of doing it in all situations is using this pore-based thinking, energy awareness, and energy kind. Thanks. These techniques I haven't had the time, but has been very successfully applied in very complicated robotic system. For example, the LR, one of the biggest lab in robotics in the world. Now, what's next? As Einstein said, logic will get you from A to B. Imagination will take you anywhere. And Leonardo da Vinci, already 500 years ago, he basically was trying to understand one of the most biggest beauty of nature, which is the bird's flight. And we have, and of course, as Aristotle says, in all things of nature, there is something of the marvelous, and you can always learn from nature, from birds, for example. We have built a robotic bird, which it's basically can go at the same speed, flopping frequency, and of a peregrine falcon, and this is unique. This bird can go outside. There are not a lot of other birds out there which are pretty amazing, but there is no one that can really fly very stably in 5 before up to 5 before wind. This is really pretty unique, and one of our spin-off is created from them. Now, we got the Tech Transfer Award, we got the Best Paper Award of 2017, a Robotics and Automation magazine, with the cover, and it is a pretty amazing system. We kind of understand more or less how it works. So this is a 2D CFD simulation in which you see that the vortices which are generated generate what are called a reverse form Kármán-Sidze stream. And thanks to this vortex generation, you have basically a jet streams that create the thrust for the system. And all animals which actually propel themselves thanks to interaction with the fluid and like fins or wings, actually they all have, there is this kind of magic number which is called the Stroudhout number, which is very known concept, is a unitless number in fluid dynamics, which is all about 0.2 or 0.4. But once again, calling Ludwig Wittgenstein, again, I think that we need to really, to understand it properly, to look at the physics of it. And, we kind of understand why in 3D, in 2D works, but in 3D we don't. So you see that in 3D, this is a slow motion of the mechanism that we managed to let it fly. You see that there is a big twist of the wings. And this big twist is also gives rise to vortices which have a 3D nature rather than the 2D nature. And in fact, if we make these wings rigid, and we put these wings rigid on the bird, a robot, it would not fly. So it's great because this would give the opportunity, and this I'm very, very happy that the European Research Council granted me an advance grant of 2.8 million to basically look at this problem and solve this problem, to really decode how birds fly. And the way we want to do it is exactly along the same line. This is, let's say, the standard form of Navier-Stokes equation, which we will not use because we completely are rewriting this equation in a coordinate-free way. But it is well known in fluid dynamics, fluid dynamics, turbulence, and all these things are a very complicated subject. And we need a new paradigm. And as Robert Kennedy said, there are those that look at things the way they are and ask why. I dream of things they never were and ask why not. And we want to use this paradigm, the new paradigm of port-based, in order to solve this problem. Basically, in a nutshell, what we want to do with this ERC is basically to model the bird by really looking at the interaction of various parts. So the interaction between the wings and the body and the tail, is pretty simple. There are motions which are considered rigid body relative motions, and then so far it's nothing new. But things get much more complicated. If you want to basically couple the fluid dynamics to the motion of the wings, which, by the way, moves within the wind and it deforms. So you really need to extend those concepts of ports, not from finite dimensional Lie groups, but to go to infinite dimensional Lie groups. And then you need Grassmannian algebra and other kind of very cool and elegant mathematics in order to be able to basically study PDE, partial differential equations, and actually not only, but also the coupling of PDEs, which relate, for example, the fluid dynamics to the deformation of the wing in a bidirectional way. So the wind affects the deformation of the wings, and the wings, the way they move, they create and modify the flow. And furthermore, these two PDEs have a boundary in common, which is the layer, basically the surface of the wing. But this boundary moves within the state space because the wing moves within the fluid. So this thing is pretty complicated, but I think we will solve that very elegantly. And then you will have a way to really tackle things in a completely coordinate-free, interconnection, physically based, energy-based way.
Working in aviation, waste management, or agriculture, one knows that birds can be of great nuisance. Birds spread diseases, pick up waste, and pollute the surroundings. Nothing, however, tops the risk of bird strikes in aviation. Clear Flight Solutions has the answer to your problems: the Rowbird. The Rowbird is an environmentally friendly solution for all your bird-related problems. It is a flapping wing robotic bird that not only looks like a bird of prey, but also flies like one. We have many years of experience in unmanned aviation and bird control. Our certified pilots are experts in flying our Rowbirds. As safety is paramount, our Rowbirds are equipped with state-of-the-art autopilots, GPS, and geofence systems. We make sure that the pilot in command is always in control. The instinctual behavior of birds when confronted with a predator is flocking together for maximum safety. By flying around the flock, the pilot can remove the birds lastingly in the direction of choice. Shortly after this, birds will start to recognize the area as a territory of prey and will start avoiding it. By mimicking nature, Clear Flight Solutions creates a unique bird control system that birds will never get used to. We make sure your skies stay clear.
And even if now you saw it is tele-operated, this can all completely already go in autonomous mode. So I would like to conclude by citing Peter Drucker and saying, the best way to predict the future is to create it. And that's what we're trying to do with this bird. And even if some users have still problems getting used to robots, as you see here, I think that my motto has always been, the sky is not the limit, but just the first layer. Thank you very much for your attention.
Dear Stefano, thank you very much for your brilliant lecture. I hope all of participants enjoyed. And in fact, we have a lot of questions to you.
And I've started already answering some by the chat.
Yes, let me repeat these questions, and your answers will be saved in the history with your voice and smile. Dr. Kapitonov, Alexander Kapitonov asked you, thanks for the lecture. What do you think about the entropy system? When we have a dynamic movement, only energy transfer, how to choose state vector and function?
Well, if I understand the question, an entropy system is basically a system which doesn't have a symplectic structure, so in which you have a dynamic passing between the dual energy domain. So in that case, basically the state would be the equivalent of the entropy. So the entropy would be the state. So you have a number of elements that can only go in one direction, if you wish. And that is a very specific dynamical system, which is treated very elegantly. A lot of nice work is actually using contact structures now being done by Arjen van Schaft and co-operators. So this is not a problem. If I understand the question, what you mean with entropy system is the states will be in a thermodynamical system, the natural states for the storage of the only element, it would be the entropy, because every domain has duality, but the only domain that does not have duality in physics is the thermal domain, which only has entropy as a state.
Okay. Professor Emilia Friedman asked you, what about robustness with respect to time-varying delays? How you analyze robustness?
Yeah, well, actually, with using these methods, robustness is never a problem. You can lose performance, but you never lose robustness, because due to the fact that you always, actually you build the system, you control the system in such a way that energy is always tracked, and you know that you'll never generate energy spurious. So you will never get unstable if you do things this way. Of course, if you for example would deliver, you build a controller for a robot which looks in which you think is a certain behavior, and then you can use that controller for a different robot. Okay. Still, maybe the robot will not do what you want in respect to performance, but it will never get unstable. That's what I'm trying to say. So robustness is not an issue by construction.
Okay, okay. And Jacqueline Chopin asked you, hi Stefano, how to deal with the wind variations for the robotic bird? How does this work with the energy awareness? What are the limitations in this case? And what is the long-term perspective on this matter?
Yeah, well, this is why I like the bird, because of course nature is smart, right? So what happens is there is wind. Well, wind on the bird is nothing else than a power port, in which on one side you have pressure, so you have the pressure let's say the velocity of the fluid, and the pressure on the wings, and the duality between the pressure and the basically and the velocity is the power that it goes to the bird. So the bird can, by feeling that, change its shape of the wings to minimize the pressure, for example, to get less energy from the wind, to try to avoid it, or the other way around, because of course energy it can be very useful to scavenge energy from the environment to optimize the way this energy is used, for example, to increase the height. And this is what birds do with soaring. So a long perspective is to understand this in a very port-based way, and on the and then put some intelligence on it in order that we can change the shape and the impedance of the wings in order to do what we want to do.
Okay, thank you. And Hafiz Zishan Iqbal Khan tells that, thank you, really amazing presentation. Michele Cucuzella, I'm not sure that I pronounce it, Italian name.
Cucuzella.
Cucuzella, but I know that exactly Michele. Yesterday we talked with him. Thanks a lot, Stefano, for your very interesting presentation. Can you comment on the possibility of interconnecting a cyber system with a physical one? In other words, do you see a way to get an energy interpretation of the shared information?
Yes, this is what I presented as passive sampling actually does that. So, I mean, one thing also I've been trying to do, I didn't invest much time in this, use it, look into Shannon and really to bring this idea of duality in information science, but I haven't pursued that, so I stopped. But I definitely, the idea can be done to go from a digital control to a continuous time control. You could generalize this. The only thing you need is basically the fact that you want energy conservation. So if you have a system which is, you know, a cyber system and a physical system, you want that where they are interconnected and the energy flows, that in the cyber system, you have a quantity which you call energy, which is basically consistent in such a way that the transfer in one direction or the other does not create or does not dissipate energy. And then on the side of the cyber system, you could create duality of things in the way you want.
And Alexander Kapitonov insists in his discussion, and he asks you, but what to do with asymmetry of energy systems?
I don't understand the question. What to do with asymmetry energy systems? I don't understand the question.
Okay, then I have my personal question. I have actually two questions. One question close to joke, and one question maybe philosophical, serious one. Let me start from easy question. How did you protect your robot bird against crash? For example, how the control system knows that which maneuver the bird should do to avoid fall down on the earth, on the ground? How it's very fast system, very extremely.
It's mechanically robust, but of course it happens that you can break things. And so basically the idea you need an autonomous. The landing basically is the problem, right? So the system can soar without flapping. So at a certain point you can glide and come down. That's the way it basically lands at the end. So you could automate and make, you know, a kind of margin of control that when the battery, for example, the communication is lost, okay, that there is an autonomous control that basically tries to glide down and basically land flat, so to prevent that it breaks. That is what could be done.
So the robot feels the altitude and can
well, it can GPS. The robot has GPS. A GPS and IMUs, so you know the orientation of the bird all the time. It knows it, and it knows where it is by GPS because it flies outdoor. So in that case, you know everything basically. And then one thing that we do not have, but that's certainly something we want to look with specific new cameras which are out there, is you can use cameras also when you are close to the ground to use a visual flow of the motion with respect to the ground or altitude by using epipolar geometry of the vision. And in that respect, there are now some cameras that are called event cameras, which are actually neuromorphic cameras that only injects motions, and that is something that actually is the way, because otherwise with the vibration of the bird, you would always have blur in your image if you would use normal cameras.
Let me ask you one question, which is just appeared now. You tell us the theory how to parameterize the energy flows and how to control, how to understand what happens in interconnection between humans, robots, between joints in robots, and how to make this interconnection more flexible, more convenient. And my question is, and the next, your question, what is the future? As usual, future is not above the sky. Future brings new surprises between humans. And if we consider the energy flows between, emotional energy flows between humans, is it possible to parameterize? Is it possible to find some equations which will describe these emotions between humans, like the energy flows? We speak with you and we interconnect by some energy. Is it possible to parameterize this? And is it possible to control this or understand how to avoid some conflicts, how to make people more happy using your energy interconnection approach?
Well, this is a philosophical question, I would say. But
I told before.
I think that I mean the bottom line is like in this way of thinking is that you structure equation. I don't like personally equations that are just algebra. A structure gives you insight, and thinking in a port base for physical system gives you insight because it uses the very basic concepts of which physics is all based upon. Okay. For emotional, of course, energy is not, I mean, if you would be able to characterize energy of emotion, of excitements, why not? You could do that, and you could definitely define system theoretical models of it. I mean, there are people that have been using these things for economics, you know, by defining proper energy functions, if you wish, and conserve quantities. I mean, the fact that you basically use conserved quantities, and, you know, it is well known that the energy is conserved because the law of physics are constant in time, and that's an Noether theorem. But of course, you could use these paradigms and extend into different situations in psychology or economics or whatever.
Okay.
And also in quantum mechanics, by the way, which is something which actually I'm doing now. I see a question related to quantum mechanics. I'm actually working with a theoretical physicist now, who's really amazed about this way of thinking, and we want actually to work on quantum mechanics as well.
So you already replied, yes. So quantum mechanics also of your interest in the future.
Yes, definitely. And of course, things will be a bit different, but there will be a lot of information stochastics and, you know, entanglement and all these things. But I have ideas. We have ideas how this could be used for it.
Stefano, thank you very much. Grazie mille. Fantastic, brilliant lecture and very interesting discussion, open discussion. So I'm very happy that it happened. So see you next time in next sessions and next visits. So thank you very much. Thank you very much for everybody who participated in our session. So unfortunately, we have to finish this session.
Thank you very much. I appreciate the opportunity, and we'll be in touch. Take care, everybody. Thank you.